So what we have learned so far is the kinetic energy. We also have to need to know the potential energy. So for potential energy, we are going to do it later. So we look at this kinetic energy and how the kinetic energy is converted to the work done. Once this kinetic energy is converted into work done, they call it non-conservative. That means the energy, I mean, of course, energy is conserved, but it is changed to other forms which we cannot recover back, like heat energy, sound energy, and so on, some other form which we cannot recover back. So they say it is non-conserved. It is not conserved. Okay, so before we go on with that, we look at this, how the kinetic energy is converted into work done. That is the work done to overcome the friction. Okay, so you read that, you read this example. Suppose a car,
Suppose a car traveling at the speed v skids a distance up d after it breaks lock. Estimate how far it would skid if it were traveling at speed 2v when it breaks lock.
okay, so now when the car is traveling at a certain speed v, the distance it covers before coming to a stop under the friction of the brake, friction of the tire, and so on. Now here they say brake lock, that means it's skidding, so there's no work done against the brake, the friction of the brake. So it's entirely the work done against the friction of the road. So the tire is rubbing against the road and it will come to a stop after a distance of small d. So that is the question. So one more time, the car, when the brake is jammed, when the brake is locked, so the frictional force from the brake pad is not working anymore. So it depends entirely on the friction between the tires and the road and the surface of the road. So this friction will cause the car to stop after a distance of small d if it is traveling at a velocity of v. Okay. Now, in the second case, when the car is traveling with a velocity of 2v, how much is the distance covered before it comes to a rest? Before it comes to a rest. So we assume that the friction is the same. The frictional force is the same. They are the kinetic friction between the tires and the road. Okay, now how to relate these two cases and find out the relationship between the distance in the second case and the distance in the first case. In the first case, we have velocity of v and the distance covered is d. In the second case, the velocity is 2d. I don't know how much is the distance covered in relation with the d here. So I call it capital D first, right? So I try to find out the relationship between the capital D and the small d here. Now, how to relate them? We relate them by the work done against friction, the kinetic energy and the work done against friction. So we look at the first case, we say that all the kinetic energy possessed by the car is used up to overcome the friction. So what is the kinetic energy the car possess? So it will be half mv square. Finally, it will come to a rest. So half mv, m0 square. Because the final velocity is 0, so the entire kinetic energy of half the mv square is used as work done to overcome friction. So half mv square is now F times d, if F is the kinetic friction and d of course is the distance traveled here, making the frictional force the subject of the formula, right? From this relationship here, I make F the subject of the formula. So I know that the frictional force is mv square over 2d, over 2d. So I keep this F equals to mv square over 2d. Just keep it first. Then I look at the second case. The second case, I apply the same reason, the same logic. The kinetic energy will be the distance multiplied with the force. This is the work used to overcome the frictional force. Okay, now the kinetic energy is half m. Now instead of v, it becomes 2v. So the kinetic energy possessed by the car is half m 2v square. 2v square. The final kinetic energy, because it come to a rest, so the final kinetic energy is 0. And this will be equals to the force multiplied with the distance. The force multiplied with the distance. The work done against friction. The entire kinetic energy possessed by the car is used up as friction, used up as work done against friction. So I try to simplify this. It becomes 4mv square over 2, and that will be Fd, right? Now, earlier on, I know the F is actually mv square over 2d. So instead of writing F here, I write down over here, instead of writing F here, I write down mv square over 2d, because I have found out what is the frictional force in the earlier case, from the earlier case. So I substitute this frictional force into the equation here. So finally, you see that they can cancel off. The mv square and mv square can cancel off. The 2 and the 2 can cancel off. So you get a very nice relationship. The distance traveled by the car in the second case divided by the distance traveled by the car in the first case is equals to 4. So the stopping distance in the second case is 4 times the stopping distance in the first case. So this is the relationship between the two distances, right? So the relationship is, in the second case, the distance used or the distance traveled before stopping is 4 times the distance traveled before stopping in the first case. Now, why is it so, right? Now, because we are traveling at a higher velocity in the second case, 2v, 2v. So we expect the distance taken before it come to rest to be bigger. How much bigger, we don't know. And we see that kinetic energy is actually proportional to the square of the velocity. So when you square this velocity, 2v becomes 4v squared. Compare with the first case is only mv squared. So actually 4 times, right? Because we square the velocity. So that's why the distance here is 4d. Right? Any questions?